Hello everyone, I am Ahmed Mustafa. I'll be presenting today an advanced image classification process that's called Spectral Angle Mapper. So what is Spectral Angle Mapper? It is a supervised image classification method that considers the image as an n-dimensional vector space and assumes the pixels as vector. It estimates the spectral angle between two pixels and then classifies the image accordingly. For example, let us assume as an image that has two bands, band 1 and band 2. Here we can see a yellow pixel that is reference of training pixel, and there is another green pixel that's from the image that we want to classify. The reflectance toward both of these pixels from band 1 and band 2 has been drawn as vector, and the angle between the two vectors can be calculated using the following function here, or the following formula. This is a cos theta function, thereby the value will range from 0 to 1, and the higher the value of the spectral angle, the higher the chances that the two pixels will fall under separate classes. And the lower the value of the spectral angle, there is a higher chance that they will fall under the same class. As you can see, there are some other green pixels here, and as all of them have the same spectral angle, they all fall under the same class. Now let's take a look at the process, how to use that in ENVI. Before we use the classification process in ENVI, we have to load the image that we want to classify, and then we go to classification, click on supervise, and select the spectral angle mapper algorithm. Then this n-member collection window will appear. As it is a supervised classification method, the user needs to provide the training information or the training data on the basis of what the classification will be done. We can do that from field survey data, or we can create our own reference or training data using image ROI. In this case, we are using the ROI. So we import the ROI, select them all, click on apply, and then this parameter setting window appears. Here we can change one parameter, that is the maximum angle threshold, which means that the spectral angle mapper will not classify any pixel beyond this threshold value. So when we select none, that means there is no threshold value of any classes. If we select single value, then it means that we define a threshold angle value for all the classes, and it's the same for every class. We can change the value in this little box here, and by default, it has been set as 0.1. If we choose multiple value, that means we can assign individual threshold values to all the classes we want. Now, instead of ROIs, we can also use spectral profile as training data, and we can do that. For example, we can click on a particular feature of the image and then view the spectral profile of that feature, and then click the option, put the plot key on, and then this XY coordinate will appear right part of the diagram. Then we can click on option again, open a blank window, drag this XY coordinate to the blank window and rename it as grass, soil, or whatever feature it is. We can do the same for all the features we want to classify, and then it will look like this. It contains all the features that we want to classify, and then we can save the diagram as a spectral library and import it to the n-member window, then use it as training data. This is just another way of using training data instead of ROIs. In this presentation, we are going to use ROIs. Now let's try the classification of the image using the default parameter setting, which is single threshold value of 0.1. So this is the image we are going to classify. This is Northern Salt Lake, and we can see the Wasatch Mountains here. It's an ALI image of Earth Observatory's satellite 1, and it has a spatial resolution of 30 meters. So as we get the output, this is what we get. We can see that there are a lot of black pixels here scattered all across the image, and it means that these black pixels are unclassified, and it does not look good for any classified image. The cyan color is residential, and it has been overclassified across the image because this is Wasatch Mountain and there is no way there should be any residential pixel. The yellow one is residential, the yellow one is grass soil, and it looks much better comparing to residential. as we compare it with the original image. And then the maroon one here is broadleaf shrub forest. This light green is irrigated park. This dark green here is conifer forest, and here is the water. And this purple one is a commercial and industry. It looks slightly good, better than residential. And I was assuming the residential feature will probably get confused with some of the other features because residential features have um, spectral characteristics of so many other features, like it has vegetations, it has concrete, commercial structures, could be. So thereby it's easier to get confused with other features. Now let's try another parameter setting. We increase the threshold value to zero point 0.2, and let's check that out. So this was for 0.1 and this is for 0.2. It looks significantly better than 0.1. As we can see, we cannot find any unclassified black pixels here. So this is much better than before, but the overclassification of residential and other vegetation covers like irrigated park has been overclassified slightly, and mostly overclassified is broadleaf shrub forest. This is not everything that's been classified as broadleaf shrub forest, definitely not the forest. Some of them are conifer forest. It got confused between irrigated park and conifer forest. Let's change the parameter to 0.3. It looks the same as 0.2. Okay, let's try 0.4. It looks the same. There is no identifiable visual changes. Now let's take a look at this table here. It shows the overall accuracy and kappa coefficient of all the threshold values we have used so far, and the uh, efficient or optimum level of overall accuracy and kappa coefficient we got is from 0.2 threshold level. It means that at 0.2 threshold value, we get the overall accuracy of 82.7 to 77%. That means that 82.7277% of those pixels have been correctly classified. While kappa coefficient of 0.7958 means it has a stronger agreement. The difference between kappa coefficient and overall accuracy is kappa coefficient considers classification by chance, and the range of kappa coefficient is from -1 to 1. So the closer it is to 1, the higher the stronger the agreement. Okay, now let's try another parameter setting, which is no threshold at all. So this is our true color composite image that we are going to compare with. And this is the classified image we got from no threshold. And it looks no different than the one we found with 0.2 threshold. Let's take a look at the overall accuracy with that. So the overall accuracy here is the same as 0.2, 82.7 to 77%, and kappa coefficient is also the same, 0.7957, and there is no unclassified pixels. And now the lowest producer's accuracy is has broadleaf shrub forest and irrigated park. The user accuracy is lowest for irrigated park, 42.17%, and broadleaf shrub forest, 75.77%. Producer's accuracy of 67.45% means that of all the as you can see in this error metrics here, there was 1212 broadleaf um, pixels, and of them only 641 of them have been correctly classified, and 572 and 73 of them have been misclassified, got confused with some other features, and 569 of those pixels have been misclassified with irrigated park. That is what we assumed before because they have similar spectral profile, and they got confused with each other. We are going to analyze the spectral profile of the of all the features here so that our hypothesis matches, or we will see about that. So the user accuracy here is 42.17%, is significantly low, and the reason behind it, we need to look further for that if it keeps on happening, then we can say for sure. Water has 100% user accuracy, and so these two, the broadleaf shrub forest and irrigated park, got mostly confused with each other. Okay, so let's try the multiple threshold value. So I tried a couple of cases for the multiple threshold value. As we saw before, irrigated park and broadleaf shrub forest got confused within each other. So I tried increasing the threshold value for them particularly and keeping the rest of the classes constant. But in that case, the overall accuracy decreased drastically, 64.3857%, and the kappa coefficient also decreased. So we increased the threshold values for all the three for all the classes respectively, and we reached the saturated level of overall accuracy that we reached before, 82.7277%, and the kappa coefficient of 0.7958. But in this case, we found some couple of unclassified pixels, and those unclassified pixels were from irrigated park and commercial industry feature. So thereby we increase the irrigated park threshold value to 0.6. Why use 0.6? Why not 0.4 or 0.5? I just increase the arbitrarily 0.6, like as we know from the threshold value definition that this is the value beyond which the algorithm will not classify any pixels. There, it means that 0.3 was not enough for irrigated park and a commercial industry. So we had to set a much higher threshold value for them. So I jumped to 0.6. And the rest of the class is 0.2, as we got the optimum level of results for 0.2, a single threshold value. And we got much better result this time. The overall accuracy is 82.72906%, and the kappa coefficient of 0.7965. So far, this is the best output we got, and this is the best parameter setting we have. Now let's take a look at the images. For case one, here we can see some black pixels, much less than the one we got from the default parameter setting, but we still have some black pixels here. And although for the default parameter setting there was a lot of unclassified pixels, but for this one, the overall accuracy kappa coefficient is significantly low, and it's very insignificant. For case two, it looks better. It definitely looks better. And here you can see that at case one, the broadleaf shrub forest has been misclassified, I mean, significantly. And the residential, although the residential is much less, the condition of residential is better here, but the forest part is worse. And in case two, it got better. Now let's take a look at the case three that gave us the best overall accuracy and kappa coefficient. As we can see here, as we can see here, it got better. The shrub forest, although it has been misclassified with lot, and we can say that from the user accuracy and producer accuracy. And the residential also got confused with so many other features. The water looks good, and the soil, grass soil feature also looks better. Now let's move on to the quantitative analysis part. And this is the error matrix of case 2 and case 3. So these were the unclassified pixels of irrigated park and the commercial industry. And in case 3, they got correctly classified, thereby increasing the overall accuracy and kappa coefficient. So this is the best outcome we got, and the users and accuracy and producer accuracy. The one other important point here, throughout all the parameters we have used, the producer's accuracy and user accuracy did not change, at all. It remains same for all the threshold values, except for the one that we got for case 1. In that case, the user accuracy and producer accuracy for irrigated park and broadleaf shrub forest were much lower than 52.89% and 67.45%. So this is the outcome with the best parameter setting. Now let's start the analysis of the error metrics. As we can see, there is like 1212 pixels of broadleaf shrub forest in the training data, and only 641 of those pixels were correctly classified. I'm talking about mostly broadleaf shrub forest here and irrigated park because they have the lowest amount of users and producers accuracy for all the threshold values we have used and all the parameter setting we have used. These two came out with the lowest users and producers accuracy. And the one other important and interesting point here is that these two features mostly got confused between themselves, other than all the other features. They also got confused with some other features, but they were like 3 or 4, something like that. As you can see, 1212 pixels of broadleaf forest, 569 of those pixels have been misclassified as irrigated park, 1 pixel as grass soil, and 1 is residential. And the same thing happened with the irrigated park. Of 639 pixels of irrigated park, 173 of those pixels have been misclassified as broadleaf shrub forest. 24 of them in residential, and 10 pixels in conifer forest, and 1 pixel in commercial industries. They also have been drastically overclassified, as we can see here. um, for the user's accuracy, 1022 of the pixels have been classified as irrigated park, and of them, only 431 of them have been correctly classified. The rest of them have been overclassified. And the same thing happened with the broadleaf shrub park. So the reason behind this significant confusion between the two features is that they have highly similar and identical spectral profile. And spectral angle mapper uses and relies solely on the spectral profile of any feature. It does not look at the band properties or anything like that. So this is one of the backdrops of spectral angle mapper, that it fails to successfully or fails to classify uh, images that have, I mean, from the similar land cover types. It cannot differentiate features from the similar land cover types like forest, grass, or parks, something like that, because they all have the similar type of spectral profile. Another interesting thing that we talked about before in the qualitative part is that residential class has 87.52% of producer's accuracy, but it was confused with almost all the other classes. And it makes sense to me because residential has a property of all the other features. It has vegetations in it, so it has similar spectral profile to some vegetations. Some other vegetation, it could have moisture in it, so it could get confused with water. And there is also concrete and structure that could get confused with industry and commercial part. The commercial and industry also got confused, but much less than the residential. So here is the overclassification slide that we already talked about. And now let's take a look at the spectral profile. This will help us understand more that why this accuracy is so low. So as we can see, the spectral profile of all the features here, you can take a look at this part of the spectral profile that they have similar kind of spectral profile of most of the features. They have the same slope, and particularly the irrigated part, the red one, and the broadleaf shrub forest, the purple one, they have the exactly identical spectral profile with similar slope, and thereby it's pretty common to have confusion between themselves. As you can see, the grass soil here has a similar profile here, but it has a different type of spectral profile right in this area and in the later part. The water spectral profile is completely different from the others, and this is why it has been classified with so much accuracy. So this is what we need to understand when working with a spectral angle mapper is we need to have features that have like dissimilar spectral profiles. Otherwise, a spectral angle mapper will not perform pretty good. So this is our summary slide. It's a quick process. It does not take much time. It took me 55 seconds in total to run the entire process. And this is the summary we got. The minimum producer's accuracy, broadleaf shrub forest, irrigated park, 52.89% and 67.45%. And the maximum producer accuracy as grass soil, 97.84%, because it did have like different spectral profile. And in the user accuracy, irrigated park has the lowest amount of irrigated park user accuracy, 42.17%, and broadleaf shrub forest has 75.77%. And the water is pretty good because of its unique comparing to other features spectral profile. And this is the parameter setting that we use to get the best output of our classified image. This is the error matrix from that parameter setting. I have marked the diagonal cells green. These are the cells that has been correctly classified. So this is the summary that I got, that broadly shrub forest and irrigated park are mostly confused within themselves, and the reason is because of having similar spectral profile with an quite identical one. The residential class is the most confused one because it has the um, mixed characteristics of all the other features. Water and grass soil have been classified with most accuracy because of their spectral profile being different to the others. And spectral angle mapper is not the best option to differentiate among similar land cover features like forest, park, and grass. So there is some other information that I think you should know, that we can make or improve the performance of the spectral angle mapper better with some additional programming, like kernel spectral angle mapper or ideal coding and adding some spatial correlation features. Instead of having all the issues that we discussed here, many people still prefer spectral angle mapper above all the other classification process because it can differentiate between two similar looking pixels. For example, if there is a shadow pixel and if there is a dark vegetation pixel, and both of them looks pretty much similar because both of them are dark, some classification may not identify or may not be able to differentiate between them. But spectral angle mapper can easily differentiate because it uses the spectral angle to differentiate. So this is all, everyone. Thank you so much. I hope I covered everything that is required for this presentation. Thank you. Good night.